probability is 0. Okay, so now that characterizes that defines a probability of an event, right? That definition actually naturally carries over to characterize a random variable. Why is that the case? Because if you have a random variable, let's say x, that maps from omega to r, or omega to the set of integers or whatever, right? I mean, as long as it maps from omega to number, it's a random variable. Now, the fact that if you take, let's say, omega inside the big omega, so basically that's all the possibilities, such that x, remember x is a map, right? It can map this omega to a real number. Let's say x is less than any number, let's say a. That's a set in omega, right? That's an event. Okay, the collection of all possibilities for which a random variable is less than a certain fixed number is an event, right? For example, let's go back to our catching the fairy example. The collection of all the possibilities that I catch the fairy within 5 minutes of its release, for example, is an event. Okay, so that's this. And this event can be measured using the probability measure, right? So this is the probability of omega in a, omega that x less than a can be, it's characterized by the probability measure. Remember, like if you have a probability measure, then for any subset of omega, that's regular enough. I don't think we want to discuss what is this regularly enough means. There is a lot of very deep measure theory that goes into that. I mean, in probability theory, it's called the measurable events. I mean, measurable subsets. This is a measurable subset, and this is defined as the CDF, or the cumulative distribution function. All right. So essentially, what's the probability that a certain random variable is less than a certain number, right? So it's called, basically, this is defined as the CDF cumulative distribution function of x. Let's see, put a subscript f here. The variable is a. Okay, and remember, the probability measure has to satisfy certain criteria. One of the criteria is that for a bigger set, the probability has to be more. Okay, and then if you look at this case, we can easily conclude that if I have b even greater than a, right, then the set that omega in omega x omega less than b, if it's less than a, then it has to be less than b, right? Because b is greater than a. Then so this less than b is going to be a superset of omega less than a, right? Which means the probability that x less than b has to be greater than the probability that x greater than a. So that means CDF of b has to be greater or equal to CDF x of a. I mean, the cumulative distribution function is going to be a non-decreasing function. Okay, so that's what cumulative distribution function has to be. Okay, so once we know this is going to be a strictly decreasing function, we can then define our last thing we want to discuss here is the PDF, is the probability distribution function. Okay, the PDF of the same random variable x at A, it's simply equal to the dA of the CDF. It's just the derivative of the CDF. And because the CDF is strictly non-decreasing, the PDF is going to be non-negative, right? So this is kind of a one-page a primer of the entire probability theory that we're going to be using in this part of 1690. Okay, we went over what is a probability space, what is random variable, it's a map from the probability space to numbers, what is an event, a subset of the probability space, and we take a probability measure on any subsets of the probability space, and then from there we can define a CDF of a random variable and the PDF of a random variable. So our tasking computational methods are usually given the probability distribution of some inputs as a random variable. We want to compute the probability distribution of outputs as a random variable. Okay,